Werner Heisenberg's introduction to the field of quantum mechanics in the early 20th century marked the beginning of a revolution in physics that fundamentally altered our understanding of the natural world. At the time, physics was dominated by classical mechanics, a deterministic framework in which it was assumed that if you had enough information about a system, you could predict its future behavior with absolute certainty. This worldview, developed by Isaac Newton in the 17th century, worked remarkably well for macroscopic objects like planets and everyday items. However, when it came to the microscopic world, the world of atoms and subatomic particles, classical mechanics was woefully inadequate. Heisenberg was one of several young physicists who recognized that something more was needed to explain the strange and mysterious phenomena observed in atomic systems. Classical mechanics, though elegant and successful in many respects, could not account for the behavior of particles at the atomic and subatomic levels. This was because the laws of motion that worked well for large objects were not applicable to particles moving at incredibly small scales. In the microscopic world, particles behaved in ways that seemed to defy the predictable, deterministic nature of classical physics. Heisenberg's contributions to this new paradigm would become central to the development of quantum mechanics, a theory that challenged traditional notions of how the universe worked. It was in 1925 that Heisenberg first made his mark on the scientific community with his work on matrix mechanics, a mathematical formulation of quantum mechanics. This was a completely novel approach to understanding the behavior of particles, and it would soon become one of the foundations of quantum mechanics. Matrix mechanics was a departure from classical physics, which relied on precise equations of motion to describe how objects move. Instead, Heisenberg's matrix mechanics focused on the relationship between different physical quantities, such as position and momentum, and how they could be described using matrices, a mathematical tool used to handle complex systems. Heisenberg's matrix mechanics was groundbreaking in its use of these abstract mathematical structures to describe physical systems. But its true power lay in its ability to provide accurate predictions of the behavior of particles at the quantum level. Prior to Heisenberg's work, the behavior of particles like electrons in an atom was difficult to explain using classical physics. In classical theory, electrons were thought to orbit the nucleus of an atom, much like planets orbit the sun, with their position and velocity being well defined at any given moment. However, experimental observations suggested that electrons did not behave in such an orderly manner. Instead, they exhibited strange properties, such as existing in multiple states at once and moving in unpredictable ways. Heisenberg's breakthrough was the realization that, at the quantum level, particles did not have well-defined trajectories or positions. Instead, their behavior could only be described in terms of probabilities. This realization marked a sharp departure from classical physics, where every physical property could, in principle, be measured with infinite precision. In Heisenberg's new framework, particles were no longer thought of as simple objects with precise positions and velocities. Instead, they were described in terms of probabilities and uncertainties. Matrix mechanics allowed Heisenberg to capture the essence of this new, probabilistic view of the quantum world. By using matrices to describe physical quantities, Heisenberg was able to show that certain pairs of physical properties such as position and momentum could not be measured simultaneously with absolute precision. The more precisely one of these quantities was measured, the less precisely the other could be known. This concept, known as the Heisenberg uncertainty principle, would become one of the most famous and controversial aspects of his work, but it emerged directly from his development of matrix mechanics. Heisenberg's contributions were not limited to matrix mechanics. He was also instrumental in developing the broader framework of quantum mechanics, alongside other luminaries like Niels Bohr, Max Born, and Erwin Schrödinger. Quantum mechanics, as it developed in the 1920s and 1930s, represented a complete overhaul of the way physicists understood the universe. It was no longer enough to describe the world in terms of classical physics where certainty and predictability were assumed. Instead, quantum mechanics introduced a new way of thinking, one that embraced uncertainty, probability, and the idea that the act of measurement itself could influence the outcome of an experiment. In Heisenberg's view, the limitations of measurement were not merely technical limitations. They were fundamental to the nature of reality itself. This was a radical shift in thinking, and it posed serious philosophical questions about the nature of the universe. If we could never know everything about a particle, if there were inherent limits to our knowledge, what did this mean for our understanding of the world around us? Was there an objective reality that existed independently of our observation, or was reality itself shaped by the act of measurement? Heisenberg's work was not only revolutionary in its mathematical, scientific implications, but also in its philosophical ramifications. The uncertainty principle suggested that the very fabric of reality was, at its core, uncertain. This stood in stark contrast to the classical physics that preceded it, which was based on the assumption that the world was knowable in its entirety. Heisenberg's realization that uncertainty was an intrinsic feature of the quantum world led to one of the most profound shifts in our understanding of the universe. The uncertainty principle introduced the idea that at the smallest scales of nature, things were not as we had once thought. There was no longer a simple, mechanistic description of the world where everything could be predicted with enough information. Instead, Heisenberg showed us that uncertainty was built into the very nature of the universe. This new view of the world was difficult for many to accept. Some scientists, including Albert Einstein, resisted the implication of quantum mechanics, particularly the uncertainty principle. Einstein famously said, "God does not play dice with the universe," expressing his discomfort with the idea that randomness and unpredictability could govern the behavior of particles. However, over time, the predictions of quantum mechanics, including those made by Heisenberg, were experimentally confirmed, and the theory became widely accepted. Today, quantum mechanics is one of the most successful and tested theories in all of science, and Heisenberg's contributions are seen as fundamental to its development. In the years following his work on matrix mechanics and the uncertainty principle, Heisenberg continued to contribute to the development of quantum theory. He worked on a variety of important problems, including the theory of atomic structure and the development of quantum field theory. He was also deeply involved in the philosophical debates surrounding quantum mechanics, particularly in his discussions with Niels Bohr. The two men had a series of intense and often contentious debates about the interpretation of quantum mechanics, particularly regarding the role of the observer in determining the outcome of experiments. These debates were not merely academic. They touched on fundamental questions about the nature of reality itself. Heisenberg's career was not without controversy, particularly in the years following the rise of Nazi Germany. Heisenberg remained in Germany during World War II and was involved in the German atomic bomb project. However, his exact role in the project has been the subject of much debate. Some historians argue that Heisenberg deliberately sabotaged the project, while others maintain that he was genuinely trying to build an atomic bomb for Germany. Regardless of the truth, Heisenberg's role in the war left a stain on his reputation, though his scientific achievements continued to be recognized. Werner Heisenberg's contributions to physics have left an indelible mark on the scientific community. His development of matrix mechanics and the introduction of the uncertainty principle forever changed the way we understand the physical world. He challenged the assumptions of classical physics and introduced a new, probabilistic view of nature. His work has had a lasting impact not only on the field of physics but also on our broader understanding of reality itself. In the end, Heisenberg didn't just make physics uncertain, he made it profoundly more interesting, more complex, and ultimately more human. Heisenberg's contributions to quantum mechanics, particularly his development of the uncertainty principle, represent a turning point in the history of physics. To understand the depth of his impact, it's essential to delve into the conceptual and philosophical implications of his work. As I continue the discussion, we'll explore the wider context in which Heisenberg's discoveries emerged, examining the challenges and debates that shaped his thinking, the controversies he encountered, and how his ideas paved the way for modern physics. Heisenberg's work emerged at a time when the world of science was experiencing rapid transformation. In the early 20th century, the study of physics was dominated by classical mechanics and the ideas of Isaac Newton. For centuries, scientists believed that the laws of motion could be applied to all matter regardless of size. The laws of classical mechanics seemed perfectly capable of explaining the behavior of large-scale objects like planets and projectiles, and even phenomena on the scale of atoms could be described with sufficient accuracy using Newtonian mechanics. However, new experimental evidence began to suggest that classical physics was incomplete and couldn't account for the behavior of particles at the quantum level. The early 1900s saw the development of theories that would challenge the very foundations of physics. Max Planck, Albert Einstein, Niels Bohr, and others began to question classical mechanics assumptions and introduced ideas that were groundbreaking and deeply radical. Planck's introduction of quantization in 1900, followed by Einstein's work on the photoelectric effect in 1905, pointed to the inadequacy of classical physics in explaining atomic and subatomic phenomena. They introduced the idea that energy was not continuous but rather came in discrete packets, or quanta. These insights led to the birth of quantum theory, a field that Heisenberg would help define in the following decade. Heisenberg's introduction of matrix mechanics in 1925 was a crucial step in this journey. Matrix mechanics was a completely novel approach to understanding quantum systems. Unlike classical physics, which focused on precise, measurable quantities like position and momentum, Heisenberg's matrix mechanics employed a radically different mathematical framework to describe the behavior of particles. It represented a departure from the deterministic worldview of classical physics, introduced a probabilistic model that reflected the inherent uncertainties of the quantum world. In many ways, matrix mechanics was the beginning of Heisenberg's most famous and influential discovery, the uncertainty principle. This principle was a direct consequence of the mathematical formulations Heisenberg developed to describe quantum systems. The uncertainty principle states that there are fundamental limits to how precisely certain pairs of properties, such as a particle's position and momentum, can be known simultaneously. The more precisely one property is measured, the less precisely the other can be determined. In essence, Heisenberg demonstrated that measurement itself affected the very state of the system being observed, a stark contrast to the classical view where measurements could be made with perfect precision without influencing the system. Heisenberg's uncertainty principle was a bold declaration that the universe was not as predictable and deterministic as previously thought. It suggested that at the quantum level, uncertainty was not just a limitation of human observation or measurement techniques, but a fundamental property of nature itself. This idea contradicted the classical assumptions that governed physics for centuries, and introduced an inherent unpredictability into the fabric of the universe. The implications of the uncertainty principle were profound, both scientifically and philosophically. On a scientific level, Heisenberg's discovery required a complete rethinking of how we describe the behavior of particles. In classical mechanics, particles were treated as distinct entities with definite positions and velocities that could be measured and tracked over time. But in Heisenberg's framework, particles could no longer be understood in such simple terms. Instead, their behavior could only be described in terms of probabilities, what was known as wave functions representing the likelihood of finding a particle in a particular state. Philosophically, Heisenberg's work shattered long-standing ideas about the nature of reality itself. In classical physics, the universe was seen as a clockwork mechanism where everything could be predicted with enough knowledge of initial conditions. Heisenberg's uncertainty principle challenged this notion, suggesting that the very act of observing a system could alter its state. This led to debates about the role of the observer in determining reality. If the act of measurement itself introduced uncertainty into the system, what did that mean for the objective nature of reality? Was reality independent of observation, or was it shaped by it? The philosophical implications of Heisenberg's work sparked heated debates with the scientific community, particularly between Heisenberg and Albert Einstein. Einstein, one of the central figures of modern physics, was deeply uncomfortable with the probabilistic nature of quantum mechanics and the uncertainty principle. He famously expressed his skepticism by saying, "God does not play dice with the universe." To Einstein, the uncertainty principle suggested that the universe was inherently random and chaotic, something that he could not accept. Einstein's views on quantum mechanics were in direct contrast to Heisenberg's, and their philosophical difference led to a famous correspondence and a series of public debates about the interpretation of quantum theory. Despite Einstein's reservations, the predictions made by quantum mechanics grounded in Heisenberg's uncertainty principle were repeatedly confirmed by experiment. In the decades following the development of quantum mechanics, scientists demonstrate that the behavior of particles could not be understood using classical physics. The development of technologies such as semiconductors, lasers, and MRI machines all relied on quantum mechanics, and they further validated Heisenberg's ideas. Quantum mechanics not only revolutionized theoretical physics but also led to practical advancements that transformed the modern world. Although the uncertainty principle was initially met with resistance, over time it became one of the most widely accepted aspects of quantum mechanics. It has become a cornerstone of modern physics, forming the foundation for many areas of research, including quantum computing, quantum cryptography, and particle physics. The principle also paved the way for new and exciting fields of study such as quantum field theory and string theory, which continue to explore the deep and strange implications of Heisenberg's work. Heisenberg's uncertainty principle also had a lasting impact on the way physicists approach measurement in quantum systems. The principle emphasized the need to account for the effects of measurement itself when studying quantum phenomena. In particular, it led to the development of a new understanding of the role of observation in quantum mechanics. Instead of seeing measurement as an external process that only reveals the properties of a system, Heisenberg and other physicists recognized that measurement was inherently tied to the system being studied. This idea formed the basis of the Copenhagen interpretation of quantum mechanics, which became one of the dominant frameworks for understanding quantum phenomena. Heisenberg's work continued to have a profound influence on the field of physics throughout his career. In the 1930s and 1940s, Heisenberg worked on a variety of important topics, including the theory of atomic structure and the development of nuclear physics. During World War II, he was involved in the German atomic bomb project, a controversial and politically charged chapter of his life. After the war, Heisenberg continued his scientific work and contributed to the development of the field of quantum electrodynamics, further cementing his place in the history of physics. Throughout his life, Heisenberg remained committed to the idea that uncertainty was not a flaw in our understanding of the universe, but rather a fundamental feature of the quantum world. He believed that quantum mechanics provided the most accurate and complete description of nature that science could offer, even if it meant embracing a level of uncertainty that was once unimaginable. In this sense, Heisenberg's legacy is one of embracing the unknown, acknowledging that there are limits to human knowledge, but also recognizing that the pursuit of understanding, despite its uncertainties, is what drives science forward. Werner Heisenberg's work in quantum mechanics and his uncertainty principle transformed our understanding of the universe. He helped to shape a new vision of physics, one that embraced uncertainty and probability at its core. His contributions are not just confined to the field of physics, they have reverberated across all areas of science and have influenced the way we think about knowledge, measurement, and reality itself. Heisenberg made physics uncertain forever, but in doing so he opened up a world of possibilities that continues to fascinate and inspire scientists to this day. Werner Heisenberg's work was transformative in the field of quantum mechanics, and the implications of his contributions extend far beyond the realm of physics. The two most significant elements of his legacy, matrix mechanics and the Heisenberg uncertainty principle, forever altered our understanding of the natural world. These ideas are deeply intertwined, and their development laid the foundation for the quantum revolution of the early 20th century. In this segment, we will explore the nature of these contributions, examining how Heisenberg's introduction of matrix mechanics and his formulation of the uncertainty principle reshaped the scientific landscape. At the dawn of the 20th century, physics was still largely governed by the principles of classical mechanics. Isaac Newton's laws of motion, which described the movement of macroscopic objects, were widely accepted and applied to a vast range of phenomena. However, when scientists began investigating the behavior of particles at atomic and subatomic scales, they encountered challenges that classical physics could not resolve. Classical mechanics assumed that the properties of objects such as their position, momentum, and energy could be known with absolute precision. Yet, at the microscopic level, this deterministic approach seemed to fail. The behavior of particles like electrons and atoms could not be explained by classical laws, and it became clear that a new framework was needed. The most notable early experiments that highlighted the limitation of classical physics were based on the study of blackbody radiation. Max Planck's work on this problem in 1900 introduced the concept of quantization, an idea that energy could only exist in discrete amounts, or quanta. Planck's solution was the first step toward quantum theory, and it marked the beginning of a new era in physics. However, it was Albert Einstein's explanation of the photoelectric effect in 1905 that demonstrated the need for a more complete quantum theory. Einstein showed that light could be understood as a stream of particles called photons, which was in direct conflict with the classical wave theory of light. By the 1920s, the quantum revolution had taken full form. Heisenberg, along with other scientists like Niels Bohr and Erwin Schrödinger, was at the forefront of this movement. While Schrödinger worked on wave mechanics and Bohr developed the Bohr model of the atom, Heisenberg focused on creating a mathematical framework that could describe the behavior of subatomic particles. His approach, known as matrix mechanics, was both innovative and abstract, and it marked a departure from the classical ideas of physics. Matrix mechanics was a completely new way of thinking about the behavior of particles. Classical physics had relied on deterministic equations of motion where particles' positions and velocities could be calculated precisely. However, Heisenberg's matrix mechanics did not rely on these traditional concepts. Instead, he used matrices, mathematical constructs, that described the relationships between different quantities in a system. These matrices represented the physical properties of particles, such as their energy, momentum, and position, but they were not intended to be exact representations of the particles themselves. In matrix mechanics, Heisenberg introduced a revolutionary idea. Instead of describing the trajectories of particles in space and time, he described the possible outcomes of measurements. The key insight was that certain quantities in quantum systems, such as position and momentum, could not be simultaneously known with perfect accuracy. This was a departure from classical physics, where the precision of measurements was assumed to be unlimited. The idea that physical properties like position and momentum were inherently uncertain at the quantum level would later evolve into Heisenberg's famous uncertainty principle. Heisenberg's matrix mechanics, although initially challenging for many to grasp, eventually became one of the two main formulations of quantum mechanics, alongside Schrödinger's wave mechanics. The two formulations were later proven to be mathematically equivalent, but Heisenberg's matrix approach had a major philosophical implication. It suggested that the very act of measuring a particle's properties could alter the outcome of the measurement. This idea was radical because, in classical physics, measurements were thought to be passive observations that did not influence the system being observed. In quantum mechanics, however, measurement was an active process that affected the state of the system itself. Heisenberg's matrix mechanics was a crucial step in the development of quantum mechanics, but it was the uncertainty principle that would cement his place in scientific history. The uncertainty principle stated that it was impossible to simultaneously know both the exact position and the exact momentum of a particle with complete precision. This was not a limitation of technology or measurement, as was often thought, but a fundamental property of nature itself. The more accurately you measured one of these properties, the less accurately you could measure the other. This idea was at odds with classical mechanics, where it was assumed that both position and momentum could be measured simultaneously with arbitrary precision. The uncertainty principle had far-reaching consequences for our understanding of the universe. In classical physics, the idea of uncertainty was foreign. If you had enough information about a system, say, the position and velocity of a planet, you could predict its future behavior with high accuracy. This determinism was a key feature of classical mechanics. However, the uncertainty principle suggested that, at the quantum level, uncertainty was built into the fabric of reality. There were inherent limits to what could be known about a particle's properties, and these limits were not due to experimental imperfections but were intrinsic to the quantum nature of particles themselves. Heisenberg's uncertainty principle had profound philosophical implications. It challenged the very idea of determinism that had been central to classical physics. If the future of a system could no longer be predicted with certainty, then what did this mean for the nature of reality itself? Was the universe fundamentally random, or was it simply beyond human comprehension? The uncertainty principle opened the door to new ways of thinking about the nature of knowledge and the limits of human perception. In addition to its scientific and philosophical significance, the uncertainty principle also had practical consequences. It became a cornerstone of modern quantum mechanics, providing a framework for understanding the behavior of subatomic particles in a way that classical physics could not. The principle was confirmed by numerous experiments, and it became an essential part of the quantum theory that would later underpin much of modern technology, including semiconductors, lasers, and quantum computers. As Heisenberg's ideas began to take hold in the scientific community, they sparked a major shift in how scientists approached the study of the quantum world. The idea that particles did not have well-defined positions and velocities, but instead existed in a state of probability, was a difficult pill for many to swallow. Some, like Albert Einstein, resisted the implications of quantum mechanics, preferring the classical view of the world as a deterministic system. However, as more experiments were conducted, it became increasingly clear that quantum mechanics provided the best description of reality at the subatomic scale. In the years following his groundbreaking work, Heisenberg continued to contribute to the development of quantum mechanics. He worked on a variety of important topics, including the theory of atomic structure, quantum field theory, and nuclear physics. Despite the controversies surrounding his involvement in the German atomic bomb project during World War II, Heisenberg's scientific legacy remained intact. His contributions to quantum mechanics, particularly the development of matrix mechanics and the formulation of the uncertainty principle, have had a lasting impact on the field and continue to shape our understanding of the universe. Heisenberg's work also opened up new avenues for scientific exploration. The uncertainty principle, for example, laid the foundation for the development of quantum field theory and quantum electrodynamics, which describe the interactions between particles and fields. These theories, along with Heisenberg's own ideas, continue to be central to the study of particle physics, cosmology, and other fields of scientific inquiry. As we look back on Heisenberg's legacy, it's clear that his contributions to quantum mechanics were not just technical innovations, they were conceptual revolutions that reshaped the way we understand the nature of reality. His work fundamentally challenged the classical worldview and introduced a new, probabilistic way of thinking about the universe. In doing so, Heisenberg not only made physics uncertain, but also made it profoundly more fascinating and complex. His ideas continue to inspire and challenge scientists, philosophers, and thinkers around the world, ensuring that his legacy will endure for generations to come. Heisenberg's contributions to quantum mechanics represent a monumental shift in our understanding of the universe. As we continue to explore his legacy, we find that the uncertainty principle and his development of matrix mechanics form the foundation of much of modern physics. These discoveries were not only groundbreaking in their scientific implications, but also in the way they challenged and reshaped the entire philosophy of science. This section will delve further into the continuing impact of Heisenberg's work, exploring the philosophical implications of his discovery, their real-world applications, and the ways in which they influence the trajectory of future scientific developments. The uncertainty principle introduced by Heisenberg did more than simply alter the way we approach physics. It fundamentally changed the way we think about knowledge and reality. In classical physics, the world was considered to be fully deterministic. If we had complete knowledge of a system's current state, we could predict its future state with absolute certainty. This idea was central to the works of Newton and other classical physicists who believed that the universe operated like a giant clock, with everything moving in a predictable, orderly manner. However, Heisenberg's uncertainty principle challenged this vision, introducing an inherent limitation to what could be known about the world at the quantum level. He showed that at the smallest scales, the universe was not deterministic but instead probabilistic, governed by uncertainty. Heisenberg's work posed a profound challenge to the philosophy of determinism that had been so deeply ingrained in science for centuries. The uncertainty principle suggested that, even if we could observe a system with perfect precision, there would always be limits to what we could know about its properties. For example, no matter how accurately we measured the position of an electron, there would always be an inherent uncertainty about its momentum, and vice versa. This limitation was not due to technological or measurement constraints, but rather a fundamental property of nature itself. In this way, Heisenberg's work introduced a new kind of epistemology, a way of thinking about knowledge that acknowledged the limits of human understanding. The philosophical implications of Heisenberg's work were not lost on the scientific community. While some physicists, including Heisenberg himself, accepted the uncertainty that quantum mechanics introduced as an inherent feature of reality, others, most notably Albert Einstein, found it deeply unsettling. Einstein, who had famously quipped that God does not play dice with the universe, resisted the idea that uncertainty was a fundamental aspect of nature. To Einstein, the probabilistic nature of quantum mechanics represents a failure to fully understand the underlying reality of the universe. He believed that there must be a more complete theory, one that could explain quantum phenomena in a deterministic way. Einstein's objections to quantum mechanics sparked a series of debates and correspondence with Heisenberg and other quantum physicists as they grappled with the nature of quantum reality. Despite Einstein's reservations, the predictions of quantum mechanics include Heisenberg's uncertainty principle were experimentally confirmed time and again. The behavior of particles at the atomic and subatomic levels consistently followed the principles of quantum mechanics, and numerous technologies that rely on quantum principles, such as semiconductors, lasers, and nuclear reactors, became essential parts of modern life. These practical applications of quantum mechanics reinforced Heisenberg's ideas and led to the widespread acceptance of the uncertainty principle as a fundamental aspect of reality. One of the most significant aspects of Heisenberg's legacy is the way in which his ideas laid the groundwork for future developments in physics. His matrix mechanics, which was the first complete formulation of quantum mechanics, became one of the two primary mathematical approaches to the theory, the other being Schrödinger's wave mechanics. While the two formulations were mathematically equivalent, they represent different conceptual approaches to understanding quantum systems. Heisenberg's matrix mechanics was more abstract and focused on the relationships between observables, such as energy and momentum, while Schrödinger's wave mechanics treated particles as waves and used wave functions to describe their behavior. The impact of Heisenberg's work on quantum mechanics extended beyond his own contributions. His ideas paved the way for the development of quantum field theory, which describes the interactions between particles and fields. Quantum field theory is a cornerstone of modern particle physics and has led to groundbreaking discoveries about the fundamental nature of matter and the forces that govern the universe. Heisenberg's work also influenced the development of quantum electrodynamics, QED, a theory that describes the interaction between matter and electromagnetic fields. QED, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, would go on to become one of the most successful and experimentally confirmed theories in physics, and it would not have been possible without the foundations laid by Heisenberg's work on matrix mechanics. In addition to his contributions to theoretical physics, Heisenberg's ideas also had a profound impact on the development of experimental techniques. The uncertainty principle influenced the way in which scientists approached the study of quantum systems. Instead of treating quantum mechanics as a problem to be solved through precise measurement, scientists came to understand that measurement itself played a key role in determining the outcome of experiments. This realization led to new experimental strategies and techniques, particularly in the field of quantum optics, where researchers began to explore the fundamental nature of light and the limits of measurement. Heisenberg's work also had significant philosophical and ethical implications, particularly during World War II. During the war, Heisenberg remained in Germany and became involved in the German atomic bomb project. The exact nature of his role in the project has been the subject of much debate. Some historians have suggested that Heisenberg actively worked to build an atomic bomb for Nazi Germany, while others believe that he deliberately sabotaged the project, either by withholding critical information or by intentionally miscalculating key components. The truth remains unclear, but Heisenberg's involvement in the atomic bomb project has sparked a larger ethical debate about the role of scientists in wartime research and the moral responsibility that come with the power to unlock the forces of nature. In the years following the war, Heisenberg continued to make significant contributions to quantum mechanics and other fields of physics. He worked on the development of quantum field theory and explored the connections between quantum mechanics and the theory of relativity. His work on the theory of nuclear forces also laid the foundation for later developments in particle physics and the Standard Model, which describes the fundamental particles and forces that make up the universe. Despite the controversies surrounding his involvement in the German atomic bomb project, Heisenberg's scientific legacy remained intact, and his work continues to shape the course of modern physics. As we look back on Heisenberg's career, we see a figure whose ideas forever altered the landscape of science. His development of matrix mechanics and the uncertainty principle revolutionized our understanding of the universe, introducing a new way of thinking about knowledge, measurement, and reality itself. Heisenberg's contributions laid the groundwork for many of the major advances in physics that followed, from quantum field theory to the Standard Model of particle physics. His work has had a lasting impact not only on science, but on the way we view the world around us. In conclusion, Werner Heisenberg's work in quantum mechanics forever changed the way we understand the universe. His development of matrix mechanics and the formulation of the uncertainty principle were pivotal moments in the history of science, reshaping the way physicists think about the nature of reality. While his ideas were initially controversial, they have since become foundational to modern physics. Heisenberg's legacy continues to inspire scientists and philosophers, reminding us of the beauty and complexity of the universe and the limits of human knowledge. Werner Heisenberg's work on quantum mechanics stands as one of the most significant scientific contributions of the 20th century. His breakthroughs not only transformed physics, but reshaped our understanding of the universe at its most fundamental level. The three key aspects of his contributions that truly revolutionized the field are matrix mechanics, the uncertainty principle, and the philosophical implications of quantum mechanics. These concepts are inseparable from one another, and together they challenge established ideas, opening the doors to a new era of scientific exploration. This segment delves deeply into the importance of these contributions, their implications, and the lasting legacy Heisenberg left on the field of physics. Matrix mechanics was one of Heisenberg's first major contributions to the quantum revolution. It was developed in 1925 during a period when traditional classical physics was proving inadequate for explaining the behaviors of subatomic particles. Heisenberg, along with his contemporaries Niels Bohr and Max Born, was seeking a way to describe atomic phenomena that were observed to behave in ways that classical physics could not explain. Classical mechanics, founded by Isaac Newton, assumed that physical systems operated according to deterministic laws. The behavior of an object like a planet or a bullet could be predicted with certainty if enough information was provided. However, this deterministic view of nature failed to account for the strange behavior of particles on the quantum level, which seemed to defy the principles of classical mechanics. Heisenberg's solution was matrix mechanics, a formulation of quantum mechanics that did not rely on classical ideas of trajectories and velocities. In matrix mechanics, Heisenberg used matrices, abstract mathematical constructs, to represent the physical properties of particles such as momentum and energy. Unlike the classical view, which treated particles as distinct entities with well-defined positions and velocity, matrix mechanics treated the properties of particles as interconnected variables represented by these matrices. The key insight here was that, rather than focusing on tracking the position and motion of a particle over time, matrix mechanics focused on the interactions and relationships between different quantities, such as energy and momentum, that could be measured. Matrix mechanics was a radically different way of thinking about the behavior of particles. It was abstract, complex, and initially difficult to understand, but it successfully explained many phenomena that classical mechanics could not. It also set the stage for a fundamental shift in physics as it moved away from the deterministic view of the universe in favor of one that was inherently probabilistic. In this framework, instead of trying to predict the future state of a system with certainty, the focus shifted to understanding the probability of various outcomes. The development of matrix mechanics was a major achievement in itself, but Heisenberg's most famous contribution came soon after with the formulation of the uncertainty principle. The uncertainty principle was a direct consequence of his work on matrix mechanics and was the cornerstone of his view of quantum mechanics. In its simplest form, the uncertainty principle states that there are fundamental limits to how precisely we can simultaneously know certain pairs of properties of a particle. The most well-known example of this is the relationship between position and momentum. According to Heisenberg, the more precisely we try to measure a particle's position, the less precisely we can know its momentum, and vice versa. This was not a limitation of technology or measurement equipment, but an inherent feature of the quantum world. The uncertainty principle represented a seismic shift in how physicists understood the nature of the universe. For centuries, classical mechanics had taught that, with enough knowledge, the future could be predicted with absolute certainty. If we knew the position and velocity of a planet, for example, we could calculate its future trajectory with great accuracy. However, Heisenberg's uncertainty principle showed that at the quantum level, this was not the case. Particles did not have well-defined positions and velocities that could be known simultaneously with perfect precision. Instead, their properties existed in a state of uncertainty, governed by probabilities. This realization fundamentally changed the way physicists thought about measurement and reality itself. In classical physics, measurement was assumed to be a passive act in which the properties of a system were observed without affecting the system itself. But in Heisenberg's quantum mechanics, the act of measurement itself was seen as actively influencing the system being measured. This idea, often referred to as the observer effect, was a direct departure from classical notions of observation. In the quantum world, observation was no longer neutral. It was an integral part of the process that determined the state of the system. Heisenberg's uncertainty principle also had deep philosophical implications. It raised fundamental questions about the nature of reality. In classical physics, there was a belief in an objective reality, one that existed independently of our observation. This view was deeply tied to the deterministic worldview that governed classical mechanics. However, Heisenberg's work suggested that reality at the quantum level was not as fixed and objective as previously thought. Instead, it was inherently uncertain and probabilistic. The precise state of a particle was not something that could be definitively known. Instead, it was governed by probabilities, and these probabilities were influenced by the act of measurement itself. The uncertainty principle also called into question the nature of causality. In classical mechanics, causality was central to understanding the behavior of systems. If we knew the initial conditions of a system, we could predict its future behavior. Heisenberg's uncertainty principle, however, suggested that causality could not be applied in the same way to quantum systems. The uncertainty in the position and momentum of a particle meant that the future behavior of the system could not be predicted with absolute certainty, even if we had complete knowledge of its current state. This was a direct challenge to the classical view of a cause and effect universe. The philosophical implications of Heisenberg's uncertainty principle were hotly debated within the scientific community. While Heisenberg himself embraced the uncertainty and the probabilistic nature of quantum mechanics, other physicists, particularly Albert Einstein, resisted it. Einstein famously said, "God does not play dice with the universe," expressing his discomfort with the idea that the universe at its core was governed by randomness. Einstein believed that quantum mechanics was an incomplete theory and that there must be hidden variables, unknown factors that could explain the apparent randomness of quantum phenomena. Despite Einstein's objections, the uncertainty principle became a cornerstone of quantum mechanics and has been experimentally confirmed countless times. The development of technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI, machines all rely on principles derived from quantum mechanics. These applications demonstrate that the uncertainty principle is not just a theoretical construct, but a real and fundamental aspect of the natural world. Heisenberg's work also had a significant impact on the philosophical and ethical considerations of science. During World War II, Heisenberg remained in Germany and became involved in the German atomic bomb project. The specifics of his role in the project remain unclear, and historians have debated whether he actively worked to build an atomic bomb for Nazi Germany or whether he deliberately sabotaged the project. This question has sparked a larger conversation about the ethical responsibility of scientists, especially when their work can be used for destructive purposes. Heisenberg's involvement in the atomic bomb project has continued to be a source of controversy, and it has raised important questions about the role of science in warfare and the moral responsibilities of those who advance human knowledge. Heisenberg's legacy is not confined to the specific discoveries he made during his lifetime, but also to the lasting impact of his work on the entire field of physics. The principles he developed in the 1920s and 1930s continue to form the foundation of quantum theory, which remains one of the most successful and well-tested theories in the history of science. His matrix mechanics and the uncertainty principle opened the door for future advancement in physics, such as quantum field theory and the Standard Model of particle physics. Furthermore, Heisenberg's work helped shape the way we think about the relationship between science and philosophy, forcing us to confront the limits of human knowledge and the unpredictable nature of the universe. In conclusion, Heisenberg's contributions to quantum mechanics forever changed the way we understand the universe. His development of matrix mechanics, the formulation of the uncertainty principle, and the philosophical questions his work raised all had a profound impact on the scientific community. Heisenberg did not merely reshape the field of physics, he fundamentally altered our view of reality itself. His work opened up new avenues of exploration, inspiring future generations of scientists to explore the depths of the quantum world. Through his innovations, Heisenberg left a legacy that will continue to influence the course of science for generations to come. Heisenberg's profound contributions to quantum mechanics forever changed how we understand the universe at its most fundamental level. His work, particularly on matrix mechanics and the uncertainty principle, disrupted century-old concepts of determinism and paved the way for an entirely new scientific paradigm. These advancements not only led to revolutionary progress in the field of physics but also challenged long-standing philosophical notions about the nature of reality itself. As we continue to reflect on Heisenberg's legacy, it becomes clear that his contributions extend far beyond the confines of science, influencing ethics, philosophy, and the way we perceive the world. Heisenberg's introduction of matrix mechanics in 1925 marked one of the earliest significant breakthroughs in the development of quantum mechanics. Unlike classical mechanics, which relied on deterministic equations to describe the motion of objects, matrix mechanics provided a new framework for understanding the behavior of subatomic particles. Classical mechanics, with its precision and predictability, assumed that if enough data were available, such as a particle position and velocity at a given time, the future behavior of the system could be calculated with certainty. However, the quantum world defied this classical approach, as particles at the atomic and subatomic level exhibited strange and unpredictable behavior. Heisenberg's matrix mechanics was born out of a need to explain this new, baffling reality. Rather than focusing on tracking the trajectory of a particle through space and time, Heisenberg's approach used matrices, mathematical constructs that represented physical quantities like energy and momentum. These matrices were not intended to represent the actual position or movement of particles in a traditional sense. Instead, they reflected the relationships between different physical properties of the system. For example, one matrix might represent the energy of a system, while another might represent its momentum. By studying how these matrices interacted with one another, Heisenberg was able to make predictions about the system's behavior. Matrix mechanics was a radically new approach to describing quantum systems, and it provided an elegant solution to many of the challenges that had previously stumped physicists. One of the key insights that came from matrix mechanics was the idea that physical property, like position and momentum, could not be precisely known at the same time. This was not simply a limitation of measurement tools or techniques, but a fundamental feature of the quantum world. In this new framework, instead of focusing on precisely calculating the future path of a particle, scientists would describe the system in terms of probabilities and uncertainties. The relationship between these uncertainties, especially between position and momentum, became Heisenberg's most famous contribution, the uncertainty principle. The uncertainty principle states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle with complete precision. The more accurately one of these quantities is measured, the less accurately the other can be determined. This groundbreaking idea introduced an inherent limitation to knowledge at the quantum level, suggesting that uncertainty is not just a product of technological limitations but an intrinsic feature of nature. The implications of Heisenberg's uncertainty principle were profound. For centuries, the prevailing belief in science had been that the universe followed deterministic laws. In classical physics, if a system's initial conditions were known precisely, its future behavior could be predicted with certainty. Heisenberg's uncertainty principle shattered this idea, introducing an element of indeterminacy and probability into the very fabric of reality. This was a radical departure from classical physics, where certainty was assumed to be attainable. The uncertainty principle raised questions about the nature of reality itself. In classical physics, reality was thought to be objective and independent of observation. A tree falling in a forest would make a sound, regardless of whether anyone was there to hear it. But Heisenberg's uncertainty principle suggested that, at the quantum level, this kind of objectivity might not hold. The act of measurement itself, whether we observe a particle's position or its momentum, could influence the state of the system. In this sense, the observer was not a passive entity, but an active participant in shaping the outcome of an experiment. This idea contradicted the classical notion of an independent, objective reality and introduced a new way of thinking about the relationship between the observer and the observed. Heisenberg's work, particularly his uncertainty principle, also had profound philosophical implications. The idea that uncertainty was an intrinsic part of the quantum world challenged the deterministic worldview that had governed science for centuries. It raised important questions about free will, causality, and the nature of knowledge. Was the universe inherently random, as Heisenberg's uncertainty principle suggested, or was there some deeper, underlying reality that remained hidden from us? These questions have continued to fuel philosophical debates, and the uncertainty principle remains a topic of discussion, not only among physicists but also among philosophers who continue to grapple with the implications of Heisenberg's work. The philosophical and scientific impact of Heisenberg's uncertainty principle was not immediately accepted by all. Albert Einstein, one of the most influential physicists of the 20th century, famously rejected the idea of inherent randomness in nature. Einstein's famous remark, "God does not play dice with the universe," expressed his discomfort with the probabilistic nature of quantum mechanics. He believed that quantum mechanics, despite its successes, was incomplete. According to Einstein, there must be some hidden variables, unmeasured factors, that could account for the apparent randomness of quantum phenomena. Heisenberg, however, was firmly convinced that uncertainty was a fundamental feature of reality, not a temporary or incomplete explanation. His disagreements with Einstein and others in the scientific community became part of the larger debate about the philosophical interpretation of quantum mechanics. Despite these debates, the uncertainty principle has been experimentally confirmed time and again. The probabilistic nature of quantum systems has been demonstrated in countless experiments, and the prediction of quantum mechanics, including Heisenberg's uncertainty principle, have been consistently validated. This has led to the widespread acceptance of quantum mechanics as the most accurate and comprehensive theory for describing the behavior of particles at the atomic and subatomic levels. The technology that has emerged from the development of quantum theory, including semiconductors, lasers, and MRI machines, is a testament to the power and accuracy of Heisenberg's insights. The uncertainty principle also had practical applications that reached far beyond theoretical physics. One of the most important contributions of quantum mechanics, and Heisenberg's work in particular, was the development of technologies that have become integral to modern life. Semiconductors, which form the basis of modern electronics, were made possible by the application of quantum principles. Similarly, lasers, which are used in a wide range of applications from telecommunication to medicine, are based on the principles of quantum mechanics. MRI machines, which are used to diagnose medical conditions, rely on the manipulation of quantum spins. These technologies, which have had a profound impact on fields such as electronics, telecommunications, and healthcare, owe much of their development to the groundwork laid by Heisenberg and other quantum pioneers. Heisenberg's uncertainty principle also played a critical role in the development of quantum computing. Quantum computers, which use the principles of superposition and entanglement, rely on the probabilistic nature of quantum mechanics to perform calculations that would be impossible for classical computers. Quantum computing holds the potential to revolutionize fields such as cryptography, artificial intelligence, and materials science. The ongoing development of this technology is a testament to the lasting impact of Heisenberg's work. In the years following his groundbreaking work on matrix mechanics and the uncertainty principle, Heisenberg continued to contribute to the development of quantum mechanics and its application. He worked on the development of quantum electrodynamics, which describes the interaction between light and matter, and he contributed to the development of the theory of nuclear forces. His work on nuclear physics, particularly during and after World War II, has been the subject of much debate, especially regarding his involvement in the German atomic bomb project. The ethical questions surrounding his role in the war continue to be a source of controversy, but Heisenberg's scientific achievements remain indisputable. As we reflect on Heisenberg's legacy, it is clear that his contributions were not only transformative in the field of physics, but also in the way we think about the nature of reality itself. His work on matrix mechanics, the uncertainty principle, and the philosophy of quantum mechanics forever changed our understanding of the universe. Heisenberg's insights laid the foundation for many of the advancements in physics that followed, and his work continues to inspire and challenge scientists to this day. Through his discoveries, Heisenberg not only reshaped the field of physics but also made us question the very nature of knowledge, measurement, and the universe. His contributions will continue to resonate throughout the scientific community for generations to come. Werner Heisenberg's groundbreaking work in quantum mechanics brought forth several transformative ideas, with each key insight reshaping our understanding of physics and reality itself. The four most crucial contributions made by Heisenberg include his development of matrix mechanics, the introduction of the uncertainty principle, the philosophical challenges his work posed, and his role in the development of quantum theory. These aspects of his work not only revolutionized the study of subatomic particles, but also set the stage for many scientific advancements in the 20th century. Matrix mechanics was the first complete formulation of quantum mechanics and represented a radical departure from the traditional, deterministic laws of classical mechanics. Classical mechanics, as established by Isaac Newton, assumed that the properties of particles, such as their position and momentum, could be known with absolute certainty. However, Heisenberg's matrix mechanics abandoned this view, focusing instead on the relationships between physical quantities. Instead of tracking a particle's position in space, matrix mechanics described how quantities like energy and momentum interacted within a system. It introduced a more abstract way of looking at particles where the focus shifted to their possible outcomes and the probabilities associated with these outcomes rather than exact paths or velocities. This approach was essential in explaining the bizarre behavior of subatomic particles that classical physics could not account for. The uncertainty principle, Heisenberg's most famous contribution, emerged from his work on matrix mechanics. It states that it is impossible to simultaneously know both the position and momentum of a particle with complete precision. The more accurately one property is measured, the less accurately the other can be known. This principle radically changed the way we view the quantum world, introducing the concept that uncertainty is a fundamental feature of nature. Unlike classical physics, where measurements were considered passive observation, Heisenberg's work suggested that observation itself could influence the outcome. This idea led to the realization that at the quantum level, particles do not exist in a fixed state until they are measured, but instead exist in a superposition of probabilities. Philosophically, Heisenberg's work presented a direct challenge to the determinism that had been the cornerstone of classical physics. The classical view was rooted in the idea that if all initial conditions of a system were known, its future could be predicted with absolute certainty. However, Heisenberg's uncertainty principle showed that this was no longer true at the quantum level. This shift raised profound questions about the nature of reality itself. If the universe was governed by uncertainty, did that mean it was inherently random, or was there some deeper truth that could explain the probabilistic nature of quantum phenomena? This idea sparked significant philosophical debates, particularly between Heisenberg and Albert Einstein, who famously rejected the concept of randomness in favor of a more deterministic universe. Finally, Heisenberg played a pivotal role in the development of quantum theory as a whole. Although matrix mechanics was a crucial part of quantum mechanics, it was not the only contribution to the field. Heisenberg's ideas were complemented by those of other physicists, such as Niels Bohr, Albert Einstein, and Erwin Schrödinger, each contributing different formulations of quantum theory. In particular, Heisenberg's interactions with Niels Bohr helped shape the Copenhagen interpretation of quantum mechanics, which emphasized the role of observation and measurement in determining the state of quantum systems. Heisenberg's contributions thus did not only consist of developing mathematical frameworks, but also of shaping the broader conceptual understanding of quantum mechanics, influencing the direction of research in the field for decades. Each of these four contributions, matrix mechanics, the uncertainty principle, the philosophical shift, and Heisenberg's involvement in the broader development of quantum theory, formed the foundation for modern physics. His work provided the necessary framework for future research into quantum field theory, quantum electrodynamics, and quantum computing. These advancements would later lead to the development of groundbreaking technologies that have become integral to daily life, such as semiconductors, lasers, and MRI machines. Through his scientific achievements, Heisenberg not only revolutionized our understanding of the atomic world, but also challenged our perception of reality itself, prompting us to reconsider the limits of human knowledge and the nature of the universe. Werner Heisenberg, one of the central figures of the quantum revolution, reshaped our understanding of the universe with his groundbreaking contributions. 5 key aspects of his work stand out: the development of matrix mechanics, the formulation of the uncertainty principle, the implications for the philosophy of science, his involvement in the German atomic bomb project, and the lasting legacy of his work in shaping modern quantum theory. Matrix mechanics, developed by Heisenberg in 1925, was the first complete formulation of quantum mechanics. It provided a revolutionary departure from classical mechanics, which had dominated physics since the time of Isaac Newton. Classical mechanics relied on precise equations to predict the behavior of particles, assuming they had well-defined positions and velocities. However, when studying subatomic particles, this framework broke down. Heisenberg's matrix mechanics, instead of tracking the exact position of a particle, focused on the relationship between physical quantities such as momentum and energy. In matrix mechanics, these quantities were represented as matrices, abstract mathematical objects that describe the system as possible states. This shift allowed Heisenberg to capture the probabilistic nature of quantum systems, laying the groundwork for a new understanding of atomic behavior. The uncertainty principle, formulated by Heisenberg in 1917, became his most famous contribution to quantum mechanics. It states that it is impossible to precisely measure both the position and momentum of a particle simultaneously. The more accurately one of these properties is measured, the less accurately the other can be known. This principle was not a limitation of measurement tools, but an intrinsic property of quantum systems. The uncertainty principle shattered the classical view that all properties of a system could be determined with enough precision. It implied that, at the quantum level, the act of measurement itself affects the system, a notion that challenged the prevailing view of an objective, deterministic universe. This idea introduced the concept of indeterminacy, where outcomes could only be predicted probabilistically rather than with certainty. Heisenberg's work also had profound philosophical implications. For centuries, science was dominated by the belief in determinism. If one knew the initial conditions of a system, its future could be predicted with certainty. Heisenberg's uncertainty principle undermined this view by introducing inherent limits to knowledge. The universe, particularly at the quantum level, was no longer seen as predictable and ordered, but as probabilistic and uncertain. This philosophical shift sparked intense debates, particularly with Albert Einstein, who rejected the notion of inherent randomness in the universe. Einstein's famous comment, "God does not play dice with the universe," reflected his discomfort with the uncertainty principle. However, despite Einstein's objections, the experimental success of quantum mechanics, grounded in Heisenberg's ideas, led to its widespread acceptance. In addition to his scientific contributions, Heisenberg's role during World War II and his involvement in the German atomic bomb project has been the subject of much historical debate. Heisenberg remained in Germany throughout the war and was part of the German nuclear research program. Some historians have suggested that Heisenberg deliberately sabotaged the project, either by withholding crucial information or by miscalculating key components, thus preventing Nazi Germany from developing an atomic bomb. Others argue that Heisenberg's efforts were sincere, and he was simply working to develop the bomb for Germany. This controversy has led to ongoing discussions about the ethical responsibility of scientists, particularly those working on military projects. Heisenberg's involvement in the bomb project remains a dark chapter in his legacy, complicating the perception of him as a purely scientific figure. Finally, Heisenberg's work laid the foundation for much of the modern understanding of quantum theory and its application. The mathematical framework he developed, particularly matrix mechanics, would go on to become one of the two main formulations of quantum mechanics, alongside Schrödinger's wave mechanics. Heisenberg's insights paved the way for further advancements in the field, including quantum electrodynamics, QAD, which describes the interaction of light and matter, and quantum field theory, which has become a central part of particle physics. The applications of quantum mechanics, from semiconductors to laser, all owe their development to Heisenberg's initial contribution. Today, quantum computing and other emerging technologies continue to build on the principles that Heisenberg helped establish, ensuring that his legacy will continue to influence science for generations to come. In summary, Heisenberg's work on matrix mechanics, the uncertainty principle, the philosophical implications of quantum theory, his involvement in the German atomic bomb project, and his lasting impact on the development of quantum theory all mark him as one of the most influential scientists of the 20th century. His contributions were not just technical, they also reshaped our understanding of reality itself, challenging established ideas of determinism and providing a new lens through which to view the universe. Heisenberg's legacy remains integral to both the field of physics and the broader philosophical and ethical discussions surrounding the role of science in society. Werner Heisenberg, one of the foremost figures in the history of quantum mechanics, made groundbreaking contributions that not only transformed physics but also fundamentally altered our understanding of the universe. His 6 key contributions to science: matrix mechanics, the uncertainty principle, development of quantum field theory, his philosophical influence, his role in the German atomic bomb project, and his lasting legacy in modern physics shaped both the course of scientific development and the way we conceptualize reality itself. These contributions remain central to many scientific advancements, continue to influence both theoretical and applied physics today. Matrix mechanics, the first formulation of quantum mechanics, was developed by Heisenberg in 1912. Unlike classical mechanics, which relied on the precise tracking of a particle's position and velocity, Heisenberg's matrix mechanics abandoned the classical notion of determinism. Instead, Heisenberg used matrices to describe physical quantities such as momentum and energy. These matrices represented not the exact state of a particle, but rather the relationships between different observables. This shift to a probabilistic framework was a radical departure from classical physics and laid the foundation for quantum mechanics. Matrix mechanics was a mathematical breakthrough that allowed Heisenberg and his contemporaries to model subatomic particles in a way that had never been done before, leading to a deeper understanding of the atomic world. The uncertainty principle, formulated by Heisenberg in 1927, is perhaps his most famous contribution to science. This principle states that there is a fundamental limit to how precisely we can measure certain pairs of properties of a particle, such as position and momentum, simultaneously. The more accurately one property is measured, the less accurately the other can be known. This principle shattered the classical worldview that believed in the possibility of perfect knowledge and prediction. In classical mechanics, if a particle's position and velocity were known, its future behavior could be determined with certainty. Heisenberg's uncertainty principle, however, demonstrated that at the quantum level, particles do not have exact, deterministic properties. Instead, they exist in states of probability. The uncertainty principle was a groundbreaking shift in our understanding of nature, challenging the idea of a clockwork universe and introducing the concept that some level of randomness and uncertainty is inherent to the universe. Quantum field theory, a major area of physics that studies the behavior of fields and particles, owes much of its development to Heisenberg's work. Heisenberg was one of the early contributors to quantum electrodynamics, QAD, a theory that describes how light and matter interact. His work in the 1920s and 1930s on the behavior of quantum fields laid the groundwork for the field. Quantum field theory would later become one of the most important areas of modern physics, providing the framework for understanding fundamental forces and particles. The development of the Standard Model of Particle Physics, which describes the fundamental particles and forces of the universe, is built upon the principles that Heisenberg and others pioneered in the early days of quantum mechanics. Heisenberg's work also had deep philosophical implications. Prior to his contributions, physics was largely deterministic. Classical mechanics, which dominated the field for centuries, assumed that if we knew enough about the initial conditions of a system, we could predict its future state with certainty. Heisenberg's uncertainty principle, however, introduced the idea that the universe, at its most fundamental level, is probabilistic. This shift raised important questions about the nature of reality. Was the universe inherently random, or did our inability to predict its behavior simply reflect the limits of our knowledge? These questions sparked heated debates within the scientific community, particularly between Heisenberg and Albert Einstein. Einstein famously rejected the probabilistic nature of quantum mechanics, but the experimental success of quantum theory gradually led to its acceptance. The philosophical implications of Heisenberg's work continue to shape our understanding of knowledge, observation, and the nature of the universe itself. Heisenberg's involvement in the German atomic bomb project during World War II is a controversial and complex aspect of his life. While Heisenberg was not directly responsible for the development of the bomb, he played a significant role in Germany's nuclear research efforts. Some historians argue that Heisenberg deliberately sabotaged the project either by failing to provide critical information or by miscalculating key components. Others maintain that he was genuinely working on behalf of Germany's nuclear ambition. This controversy has sparked ongoing discussions about the ethical responsibility of scientists, especially when their work has the potential for mass destruction. Heisenberg's role in the atomic bomb project remains a topic of debate, as it complicates his otherwise brilliant scientific legacy. Finally, Heisenberg's lasting legacy is profound. His work not only reshaped the field of quantum mechanics, but also laid the groundwork for many of the most important discoveries in modern physics. The development of quantum computing, advancements in semiconductors, the field of quantum cryptography, and technologies such as MRI machines are all direct consequences of Heisenberg's ideas. His work in quantum mechanics continues to inform research in particle physics, cosmology, and quantum information theory. Heisenberg's ability to challenge classical ideas and introduce new concepts, such as probabilistic behavior at the quantum level, continues to inspire scientists today. His contributions extend beyond the realm of science into broader philosophical and ethical domains, making his legacy a lasting influence in multiple fields of study. In conclusion, Heisenberg's contributions to matrix mechanics, the uncertainty principle, quantum field theory, the philosophical rethinking of reality, his involvement in the atomic bomb project, and his enduring legacy in modern physics have all had far-reaching effects on science and philosophy. His work helped shape the course of 20th century physics, and its influence continues to be felt in contemporary research. Heisenberg's ability to introduce uncertainty into the core of scientific inquiry not only advanced our understanding of the quantum world, but also opened up new ways of thinking about the nature of knowledge, reality, and the universe itself. Werner Heisenberg's contributions to quantum mechanics have forever altered the landscape of physics, establishing him as one of the most influential figures in the history of science. His work on matrix mechanics, the uncertainty principle, quantum field theory, the observer effect, his philosophical challenges to classical ideas, his involvement in the atomic bomb project, and his lasting legacy collectively shaped the development of modern physics and our understanding of the universe. The first major contribution Heisenberg made was in the development of matrix mechanics in 1925. This was the first complete formulation of quantum mechanics, created in parallel with Schrödinger's wave mechanics. Matrix mechanics was groundbreaking because it provided a new way of describing atomic and subatomic phenomena. Unlike classical mechanics, which assumes that particles have precise, predictable position and velocities, matrix mechanics embraced the probabilistic nature of quantum systems. Instead of focusing on precise particle trajectories, Heisenberg used matrices to represent physical quantities such as energy and momentum, and these matrices described how particles interact. This shift away from classical mechanics marked a radical departure from the deterministic worldview that had governed physics for centuries, replacing it with a more abstract, mathematical understanding of the quantum world. Heisenberg's second key contribution, the uncertainty principle fundamentally challenged classical ideas of determinism and measurement. Formulated in 1921, the uncertainty principle states that it is impossible to simultaneously know both the exact position and momentum of a particle with absolute precision. The more accurately one of these properties is measured, the less accurately the other can be known. This was not a limitation of technology or measurement tools, but a fundamental property of nature. Heisenberg's uncertainty principle shattered the classical belief that all aspects of a physical system could be known with certainty, and that the future could be predicted if enough data was provided. At the quantum level, uncertainty and indeterminacy replaced certainty, prompting a complete re-evaluation of how we understand the universe. The third contribution, quantum field theory, was another area where Heisenberg played a pivotal role. Quantum field theory describes the interactions between particles and fields and forms the foundation of much of modern physics. Heisenberg's early work on quantum electrodynamics QED, which deals with the interaction of light and matter, laid the groundwork for later developments in quantum field theory. QED would later become a central part of particle physics and is considered one of the most successful theories in science, accurately predicting the behavior of particles and fields with astonishing precision. The foundational ideas Heisenberg introduced in quantum mechanics made this later development possible, influencing key discoveries in particle physics and the Standard Model. Heisenberg's fourth key contribution, the observer effect, arose directly from his uncertainty principle. This effect suggests that the act of measurement in quantum mechanics does not merely reveal information about the system but also alters the system itself. In classical physics, observation was considered a passive act. An observer could measure a system's properties without affecting its behavior. However, in quantum mechanics, the observer plays an active role in determining the state of a system. This idea was not easily accepted as it contradicted centuries of scientific thought. Heisenberg's work challenged the very nature of reality, suggesting that the act of observing something at the quantum level is inseparable from the phenomenon being observed. Philosophically, Heisenberg's work posed significant challenges to the prevailing ideas of reality. The uncertainty principle not only reshaped physics, but also forced philosophers to rethink the nature of knowledge and existence. For centuries, the classical worldview held that the universe was predictable, that with enough data, the future of any system could be determined. Heisenberg's discovery of inherent uncertainty in the quantum realm undermined this deterministic view. If uncertainty was intrinsic to the nature of particles, could it be that uncertainty also played a role in the macroscopic world? Heisenberg's ideas challenged not just the assumptions of science, but also the way humans perceive and interact with reality. His work created a philosophical debate about whether the universe is fundamentally deterministic or probabilistic, and it continues to shape discussions in both physics and philosophy. In addition to his theoretical contributions, Heisenberg's role during World War II added another layer of complexity to his legacy. He remained in Germany during the war and worked on the German nuclear weapons program, an involvement that has been widely debated. Some historians argue that Heisenberg deliberately sabotaged the project, either by withholding key information or miscalculating important aspects of the bomb's design. Others suggest that Heisenberg genuinely tried to build an atomic bomb for Germany, but his efforts were unsuccessful. This controversy raises ethical questions about the responsibility of scientists in wartime, especially when their work can lead to devastating consequences. Heisenberg's involvement in the German atomic bomb project complicates his legacy, as it brings into focus the moral dilemmas faced by scientists during time of conflict. Heisenberg's lasting legacy is found not only in the development of quantum mechanics but also in the technologies that emerged from his theories. Quantum mechanics, with its roots in Heisenberg's matrix mechanics and uncertainty principle, has led to numerous technological advancements. These include semiconductors, which are essential to modern electronics, lasers used in everything from telecommunications to medicine, and MRI machines, which revolutionized medical diagnostics. Heisenberg's work helped to establish the theoretical framework for the technologies which continue to play a central role in modern life. His ideas also paved the way for emerging fields like quantum computing, which holds the potential to revolutionize industries from cryptography to artificial intelligence. In conclusion, Heisenberg's contributions to quantum mechanics were not just a scientific revolution, they were a philosophical and ethical shift that has had far-reaching implications. Through his development of matrix mechanics, the uncertainty principle, quantum field theory, the observer effect, his challenges to classical philosophy, and his controversial role during World War II, Heisenberg changed the way we think about the universe. His legacy, both scientific and moral, continues to shape the direction of modern physics and our understanding of the world. His work challenged fundamental ideas about determinism, measurement, and reality itself, and his contributions remain integral to the study of quantum mechanics and the technologies that have emerged from it.